Hello everyone, my name is Lalmuanchhana, a research scholar in the Department of Physics, Mizoram University under the supervision of Professor R.C. Tiwari. Today I will do a voice narrated presentation of my synopsis, and the title of my synopsis is Ab initio investigations of zinc oxide monolayer and its dope structure for spintronics and other application. Now I would like to express my gratitude to my supervisor and other members of committee for understanding my inconvenience. Now let me highlight what I will be presenting today. First, I will do a brief introduction on the work and then the scope of our study. After that, some of the work in this field and then the objective of our proposed work and the theory on which it is based. Then the tentative chapterization of my synopsis will be given. Now, what is a monolayer? A monolayer is a single layer of atoms in a two-dimensional hexagonal lattice, and we are proposing to study such structure for spintronics. And spintronics is a study of intrinsic spin of electron and its associated magnetic properties. It is believed that the future spin-based electronic devices will outclass conventional charge-based electronic devices, as conventional charge-based devices rely on charge carriers. So scientists are trying to exploit the spin rather than its charge due to its lower power consumption, faster switching time, and higher efficiency. Now back to the monolayer. The success of Geim and co-workers in 2004 in isolating a single layer samples from graphite, which were first thought to be thermodynamically unstable at finite temperature, led to a significant advances in unveiling its remarkable properties. The image shows the structure of graphene, a single layer of carbon atoms, and a ZNO monolayer. This graphene has high charge carrier mobility, high thermal conductivity, and excellent mechanical flexibility. And we are showing the monolayer of zinc oxide as well. Why zinc oxide monolayer? The great success of graphene has been followed by an equally impressive search for the development of other two-dimensional materials. Recent works have reported that ultra-thin films of ZNO and ZNS, zinc sulfide, has lowest energy in graphitic structure, indicating graphene honeycomb structure formation in such materials. Also, bulk structure ZNO is a direct wide bandgap semiconductor, which is about 3.37 electron volt, transparent in the visible wavelength range, and it is suitable for UV, ultraviolet, and blue wavelength optoelectronic application, with a large exciton binding energy of 60 millielectron volt, which enables efficient excitonic emission at room temperature. Its low refractive index, which is about 2.05, also enables easier light extraction from an optical device. Study also shows ZNO has large piezoelectric constant, resulting in strong piezoelectric polarization in the material, making the material in bulk form to be suitable for piezoelectric device fabrication, and is very promising for fabrication of high quality 2D electron gas structures. What is 2D electron gas structures? It is a scientific model in solid state physics. It is an electron gas free to move in two-dimensional but restricted in the third dimension. It has many useful and interesting properties. Now let's move to the scope of study for our proposed work. Two criteria essential for the implementation of spinning devices are effective injection of spin polarized carriers into semiconductors and high Curie temperature for material fabrication through devices. These are the criteria to be met with our proposed work. Semiconductor-based spintronics have attracted much attention because of the possibility that their spin and charge can be manipulated. However, before taking up huge projects to experimentally investigate the potential of this compound for implementation in nano devices, thorough theoretical understanding of all aspects of the material is very much needed. The proposed work will begin with a fundamental investigation of structural, optical, and electronic properties of ZNO monolayer structure. The fundamental investigation will be followed by manipulation of charge distribution and spin states through vacancy defects, formation doping, and adsorption. The origin of magnetic moment and half metallic behavior will be investigated for each of the proposed structure under such vacancy defect, doping, and absorption. Our work will attempt to find suitable ways to enhance the magnetic properties without significantly large doping that may have resulted in significant structural changes. The implementation of the first principle calculation will provide an insight of the material's properties in relation to piezoelectric and spintronic behavior. Then, interaction of atmospheric gas molecules such as ammonia, nitrogen oxide, etc., and some of the toxic gases with the monolayer of the ZNO will be investigated to explore the potential of the proposed materials for gas sensing applications. Also, the piezoelectric coefficient will also be calculated for different structure with vacancy defects and doping. Ways to enhance the piezoelectric nature by modification of the optimized monolayer compound will also be one of the main focuses of the thesis work. This investigation will serve as a challenge and motivation for other researchers in searching for new technological development. Now let me highlight some of the work that has been published in this field. Back in 2006, Tu and his colleague found that some ZNO thin films prefer a graphite-like structure, a monolayer structure, rather than the urzite structure, which were much more flexible than graphene in elasticity and better than boron nitride single layers in respect of its piezoelectric behavior. Topsakal and his team in 2009 also found that through this single layer of ZNO and bilayer of ZNO in honeycomb structure were in fact quite stable, and the honeycomb structure were not deformed in their simulation condition. They also reported that zinc vacancy resulted in magnetic moment due to the unpaired electrons of oxygen atoms around the Zn vacancy. Khan and his team also recently found that fluorine atoms form stable bonds only with zinc atoms on a graphene-like ZNO single layer, which result in one unpaired spin at each O atom. In the band structure, they also found that while the up spin channel has a band gap, the down spin channel has partially filled bands. Fluorination of ZNO single layer was found to cause the downspin oxygen through p states partially empty. On that same year, Chen and his co-workers also found that pristine ZNO layer forms stable hexagonal graphitic structure with shortened intralayer ZNO distances and elongated interlayer ZNO distance. They also found that fluorination from one side turned the planar few ZNO layers back to the urzite-like corrugated structure with enhanced stability. Half metallicity was also achieved in their density functional theory calculation for layers less than 4. Now the main objectives of our thesis. First, we'll have to investigate the structural, mechanical, and optoelectronic properties of the proposed zinc oxide monolayer. This will include all the basic properties such as each formation energy, each bond stability, each bond angle, each magnetic moment, and other such basic properties. Then we'll have to investigate the piezoelectric properties of the monolayer zinc oxide and extending the investigation with an objective of improving each piezoelectric property with doping and induced structural defect. And then we'll have to investigate the half metallic magnetism in the proposed material under substitutional doping and absorption of other elements. Recent works have already shown that this substitutional doping and absorption give rise to half metallic magnetism in such layer. And then in the last we'll have to investigate the potential application of ZNO monolayer structure for gas sensing as well. Now I will give the theory on which our calculation is based. The first principal calculation is based on a density functional theory which is developed by Kohn and Sham. Density functional theory is a computational quantum mechanical modeling method used in physics, chemistry, and material sciences to investigate the electronic structure or nuclear structure, principally the ground state, of many body system, in particular atoms, molecules, and the condensed phases. We all know since Schrodinger equation is only applicable for one body system, density functional theory has to be implemented for studying many body system. The equations are given in the slide with different functional, but I will not go detail into the equation. Just a brief overview of what the theory works on, because even the theory itself will be too long for a single presentation. So, by using this theory, the properties of many electron system can be determined by functionals, that is, functions of another function. In the case of DFT, these are functional of the spatially dependent electron density. In this theory, the total ground state energy of many electron system is a functional of the density. So, if we know the electron density functional, we know the total energy of our system. By focusing on the electron density, it is possible to derive an effective one electron type Schrodinger equation. Now we can write the total energy of our system in terms of which are all functionals of the charge density as ion-electron potential energy, ion-ion potential energy, electron-electron energy, kinetic energy, or exchange correlation energy. Approximations such as local density approximation LDA and general gradient approximation GGA are employing to refine the density functional theory results. In this work, the theoretical calculation will be performed using Vienna Ab Initio simulation package provided by Media-A. All the calculations will be done by coding using this software. Now the tentative chapterizations of the thesis. The arrangement will be as follows. Chapter 1 will contain the introductions of the present studies. It will also include the review of literature related to the present research work. Chapter 2 will contain description of the tools for investigations of the proposed studies. It will contain concise description of the methodology including DFT and how the structural, mechanical, and other properties will be investigated using DFT techniques as implemented in Media-A vast bundle software. Chapter 3 will contain all the results of the fundamental investigations on ZNO monolayer. It will contain structural, mechanical, thermodynamical, and electronic properties of the pristine ZNO monolayer. This chapter will also contain the results of the investigations on the effect of strain on the ZNO monolayer as well. Chapter 4 will contain the results of all investigations on doped ZNO monolayer. This will give valuable information on the piezoelectric property, half metallic behavior, and magnetism of doped ZNO monolayer. Chapter 5 will then contain the investigations of ZNO monolayer with adsorption of various elements and shall also include the gauge sensing properties of the materials. And on the last chapter, chapter 6, it will contain the conclusion and the future scope of the present research work. This will be followed by references and appendices. Here is some of our recent work using our software to give you an idea about our proposed work. The band structure of zinc oxide monolayer and its dope band structure when it is doped with carbon, and its magnetization density and its electron localization function. You can notice the changes in the band structure when it is doped with carbon, and also the changes in magnetization density when carbon atom is present in the structure. Here is some of the literature that I've consulted for our proposed work. So, by using this theory, the properties of many electron system can be determined by. Thank you.